Welcome back everyone. In this lecture we will prove the Wiles theorem for sl2, namely that any finite dimensional representation of sl2 is completely reducible. So, let us start with the finite dimensional representation V. Let V be a finite dimensional representation of sl2C. So, we have this Casimir operator acting on capital V. So, that is given by C of V equal to x y v plus y x v plus of h square for all V in capital. So, we observed that this C actually commutes with the action of capital. Okay, this is something we already observed. Now, suppose if we take V to be this irreducible representation V of m, okay, if V is equal to V of m, where m comes from this z plus. So, then this C must be some scalar multiple. Okay. This must be some scalar multiple of this V of m. Why? Because C being an operator acting on capital V, C must have some eigenvalue, call it lambda. So, lambda be an eigenvalue of C. So, then look at C minus lambda times identity on capital V. So, then the kernel of this is going to be non-zero space. Okay. Since this is a non-zero space inside capital V, and this is, you can easily check that this is sl2 submodule, because C commutes with the action of sl2 and lambda identity commutes with the action of sl2. So, the difference will commute with the action of sl2. So, the kernel which is like eigen space corresponding to the eigenvalue lambda. So, that actually will be sl2 submodule. So, that is easy to check. So, that forces that V has to be equal to the kernel of C minus lambda times identity, and this argument can be generalized to any algebra or any semi-simple algebra and so on. So, this is called Schur's lemma. Okay. This is called Schur's lemma. Basically, what is Schur's lemma says, if you have an algebra and finite dimensional irreducible representation of that algebra, and you have an operator acting on that operator, let us say, commutes with the action of the algebra. So, then that operator must be some scalar times identity if that representation is irreducible representation. So, it is easy to prove, the same proof that we have given here works. So, in particularly we can actually see what happens explicitly to this lambda, because this lambda can be determined using this explicit formula of this C. So, note that this C being xy plus yx plus of time h square. So, we can pick V inside capital V being the highest weight vector, highest weight vector. Since V is equal to V of m, we know that HV will be mV and then XV will be 0. So, now let us use this formula to compute what is CV. So, CV is going to be XYV plus YXV. So, this is going to be 0 plus of times H of HV, but HV is mV. So, H square V will be m square V. So, now you can see that this is exactly equal to XYV plus of times m square V. Now, note that xy is yx plus h. So, that means xyv is going to be yxv plus hv. Now, this is 0. So, that tells you that xyv is nothing but just mv. So, then we get m square by 2 plus m times v. So, Cv is acting as this scalar m square by 2 plus m on this vector v. Now, since C acts as lambda on entire module, that forces that this lambda is exactly m square by 2 plus m. So, this is the constant that we are getting using the action of C. Okay. So, basically C is m square by 2 plus m times identity on capital V, when V is V of m. So, this is a interesting calculation. So, now if we go back to finite dimensional representation of capital V, we know that, okay. So, if we take V to be finite dimensional representation of sl2c. So, now we know that for this Casimir operator, okay, this actually this V can be decomposed into direct sum of generalized eigenspaces. Okay. So, this C commutes with the action of sl2c. So, in particularly we can decompose V into direct sum of V theta, theta runs over C. So, this is the generalized eigenspace, of course corresponding to the eigenvalue theta for the operator C. So, now we know that since C commutes with the action of sl2c, all this V theta, they are all invariant under sl2c. So, V theta is indeed sl2 submodule. Now, if you are interested in proving complete reducibility for capital V, so it is enough to consider only V theta. Okay. So, we can without loss of generality assume that this C indeed acts as the scalar. So, the only eigenvalue of C for on this module V theta is just theta. Okay. So, basically it is being generalized eigenspace corresponding to the eigenvalues theta. So, there will not be any other eigenvalue that you can have for C on this space V theta. Okay. So, without loss of generality, one can assume that V equal to V theta. So, that means C has only theta as eigenvalue on capital V. Okay. So, this assumption is reasonable because we already decomposed V into direct sum of the submodules. So, we can restrict to this submodule. So, now we already know that given any finite dimensional module, there is always irreducible submodule containing in that. So, let us take one such irreducible submodule, let us call it Vm. So, Vm let us say sits inside V. Okay. So, now if we take C restricted to this Vm, so then this is going to be operator acting on Vm. Okay. So, but we already know that C restricted to Vm, it is nothing but the scalar multiple of identity. The scalar is also given by m square by 2 plus m identity on V of m. Okay. But we know that already theta is the only eigenvalue that we have on this capital V. Now, m square by 2 plus m is becomes eigenvalue for this operator C on this capital V. So, that forces that this theta must be equal to m square by 2 plus m. Okay. So, this is the conclusion that we get immediately, as theta is the only eigenvalue for C restricted to capital. So, now if we take another, let us say, irreducible representation sitting inside capital V, then by earlier argument, similar argument tells that theta must be exactly equal to n square by 2 plus n. So, that forces that this m square by 2 plus m should be equal to this n square by 2 plus n. So, now this is just a simple exercise. If you have m and n non-negative integers such that this n square by 2 plus n is same as m square by 2 plus m, then that forces that m equal to n. So, this is something I leave it as exercise. So, this exercise tells you that from this equation we get m equal to n. That means, if we take another copy of irreducible representation, some other irreducible representation inside capital V, that should be another copy of V of m. So, there is no other irreducible representation that can sit inside capital V. So, this means if V decomposes into irreducible representation, then it can only decompose as direct sum of V of m, nothing else. Okay. So, modulo the Wiles theorem, we can only have V equal to V of m direct sum some copies. Okay. So, this is what we should ultimately prove, that V is isomorphic to direct sum of V of m. So, let us see how one can obtain that. So, for that purpose we need to understand the operator H that is acting on this capital V. Okay, here is the small lemma. So, I will leave all the calculation to you. If V is a finite dimensional sl2 representation, then we can actually look at the operator H, which is acting on kernel x to kernel x, okay, where kernel x is nothing but those vector in capital V such that x v is killed. Note that to actually prove that V is isomorphic to direct sum of V of m, so we need to actually look for maximal vectors or highest weight vectors corresponding to the eigenvalue m. Okay. For that purpose, if you are interested in looking for maximal vectors, let us look at the kernel of x and then restrict the operator H on that and then see what we can actually do there. Okay. So, what we have this H, the operator, when we restrict it to kernel x, that is diagonalizable. As I said earlier, we are expecting the operator H to act diagonalizably on entire V, but for time being just we can prove that it is diagonalizable on kernel x, and then later we will actually use this to prove it is going to act diagonalizably on entire space. So, that is actually application of this theorem. Okay. So, we are proving the weaker version, but that is good enough. Okay, how one can prove this? First, to note that if I start with some w inside kernel x, then x w will be 0, then h x h w is going to be, so h x minus x h is 2x, so x h will be h x minus 2x, so that means h x h w will be h x w minus 2 x w, which will be 0 because x w is 0. So, this forces that x h w is 0, that means h w is again in the kernel of x. So, when you restrict h to kernel x, then it defines some operator on kernel x to kernel x. So, that is easy exercise, we have done it. So, now we are going to actually use some computation involving this operator x and y. So, I will leave it to you to check. So, this is a simple exercise, one can do it by induction. So, if you look at the operator x y power k, which makes sense inside endomorphism of V. So, then you can prove that x power y power k, when you are trying to commute it, then you can see that this is going to be exactly y x power k plus k into y power k minus 1 times h minus k plus 1, and this is true for all k greater than or equal to 1. Okay. So, this is something I will leave it as exercise. So, this can be proved using induction. So, now one can easily see that if we take some vector w in kernel x, so then we have, by actually repeated use of this. Okay. So, if we take x power k y power k v, then that is going to be exactly equal to k w k factorial time h into h minus 1 etcetera h minus k plus 1 w, and this is true for all k greater than or equal to 1. Okay. So, just take this formula and then just use this formula to actually prove this formula. Okay. So, this is again simple formula one can prove using the induction. Okay. So, how one can actually verify this? Sorry, I will leave it, just use induction to prove this. I will leave it to you to check this. So, how one can use this to immediately get that h is indeed diagnosable operator. So, now go back to the our operator h, which is defined from kernel x to kernel x. So, this formula tells you that x power k y power k w is given by this. Okay. So, suppose this h into h minus 1 etcetera h minus k plus 1 is 0 for all w coming from kernel x for some k. So, then that tells you that h satisfies some polynomial which has distinct roots, that will imply that h is diagnosable. Okay. So, that is what we are going to say. So, basically kernel x being actually subspace of this capital V, and V is finite dimensional representation of sl2c. So, using this one can conclude that this operator x must be nilpotent when you consider it as operator on capital V. So, look at the operator x. So, that is defined on capital V. Okay. So, now we know that h x is nothing but 2x. Okay. So, with this conditions we can actually prove that. Okay. So, I will leave it as exercise. Again, this is not very hard to prove that x is nilpotent. Actually, x acts nilpotently on capital V. Similarly, y also acts nilpotently on capital V. Maybe let me write very general version here. Suppose you have two operators, let us say E H inside some endomorphism of some W. So, but such that E H is given by some C E for some C non-zero coming from the complex numbers. So, then one can prove that C is nilpotent. Okay. So, one can adjust this scalar C and then rescale H, and then one can assume that without loss of generality E H is exactly E. Okay. So, there is this trace criterion that one can use to prove that this E is nilpotent. So, note that what is trace criterion says, okay, recall. So, trace of e power k is 0 for all k greater than or equal to 1 if and only if E is nilpotent. As long as your space is finite dimensional, of course, the dimension of W is finite dimensional, and if you work over any field, it does not matter. The trace criterion says trace of e power k is 0 for all k, that implies actually if and only if E is nilpotent. Okay. So, now using this you can conclude immediately that trace of E is 0. Now, it is a simple calculation to show that any e power k will look like commutator of two things. Okay. So, that means trace of e power k is also 0. So, it is a very simple exercise, comes from linear algebra. So, I will leave it to you to check. So, that means if we prove that means this x itself acts nilpotently on capital V and y itself acts nilpotently on capital V. So, some power of x, some power of y, especially dimension V gives you that x power dimension V, y power dimension V is 0. So, now when you restrict nilpotent operator to any invariant subspace, that will be nilpotent. So, using that you can prove that there exist n in n such that x power n, y power n, w is 0 for all w in kernel x. Okay. So, that implies that using this formula, this h, so k factorial we can forget, h into h minus 1 etc., h minus n plus 1 w is 0. So, h into h minus 1 etc., h minus n plus 1 w is 0 for all w in kernel x. So, that means this operator h satisfies this polynomial h into h minus 1 etc., h minus n plus 1. So, this is identically 0 on kernel x. So, that means the minimal polynomial of h. So, the minimal polynomial of h restricted to kernel x, so of some t, so is going to divide t into t minus 1 etc., t minus n plus 1. Since this polynomial has distinct roots, not only distinct roots, they have all roots, integral roots, okay, non-negative integers and distinct roots, that forces that the minimal polynomial of this h restricted to also has distinct roots. So, since the minimal polynomial of h restricted to kernel x has distinct roots, that forces that h restricted to kernel x is indeed diagonalizable. H restricted to kernel x is diagonalizable. So, now we have a diagonalizable operator acting on this kernel x. So, now if you are interested in finding this copies of V of m, now it is easy to do. So, since h restricted to kernel x is diagonalizable, we can actually take the eigenbasis. So, let us call V1 etc., some V r. So, this is the eigenbasis of kernel x, of course, with respect to the operator h. So, in particularly, so what will happen to this HVI? HVI is going to be some scalar. Okay. So, this scalar is going to be, let us call it lambda I Vi. Okay. So, then XVI will become 0. Okay. But this will force that the submodule generated by Vi inside capital V. So, this is actually irreducible submodule and which is isomorphic to V of lambda I. But we already know that the only irreducible submodule that can be embedded inside V is that V of m, for which that m square by 2 plus m becomes eigenvalue of that Casimir operator C. So, that forces that this lambda I must be m. Okay. So, that means h v I must be m v I for all I and x v I is 0. So, each v I indeed generates a copy of v m. Now, the claim is v is indeed direct sum of these submodule generated by v m. Okay. Each one of them indeed copies of v m. So, we have exactly r copies of v m. So, v is written as direct sum of r copies of v m. So, how one can prove that? Let's take this sum of v I ranging from 1 to r as some v dash. So, first claim is v equal to v dash. Okay. Suppose not, then v will be strictly contained in v dash, will be strictly containing v dash, that will force that v modulo v dash is a non-zero space. So, now look at that operator C, okay, because C actually leaves v dash invariant, v dash is sum of sl2 submodules. So, C leaves v dash invariant as v dash is a sum of sl2 submodules. So, then that will imply that C leaves operator on, induces operator on this quotient as well. Okay. So, since this is a finite dimensional representation, finite dimensional sl2 module, so this must have some irreducible representation sitting inside. So, there will be some irreducible module, but note that C actually will act as scalar on that irreducible representation. Let us say W, which is sitting inside V modulo V dash. So, this is irreducible, which is isomorphic to let us say some V n. So, now C is going to act as scalar, okay, when you restrict to V n. So, that is going to be n square by 2 divided by plus n into identity. So, now the only eigenvalue that C can take on capital V is m square by 2 plus m. Okay. But here we are saying that in the induced quotient we have another eigenvalue. Okay. So, that forces that both eigenvalues must be same. So, that will imply that this n is also equal to m. Okay. So, there is nothing actually you get newly. So, you will be getting this n equal to m. So, now if you go back to this copy of this W, let us say it is generated by some V bar. So, then what we can do, we can see that h V bar will be m V bar and x V bar will be 0. Okay. But if you replace this V bar by some V plus some element coming from let us say W j, where W j is coming from this, okay, what I denoted just submodule generated by V j. Okay. So, then you can see that so these are all coming from this finite dimensional representation of sl2 of C. So, indeed if you carefully analyze this irreducible representation which is isomorphic to V m. So, for any vector that is there in V m, there will be a largest power of x such that x power actually x power of that k w j, that will be inside the kernel of x. So, that means x power k plus 1 w j will be 0, okay, because it can't keep increasing. So, by putting together all of them, you can see that there exists some largest power k inside g plus such that x power k v, okay, even for v, okay, for v it is just because v is coming from capital V, v being finite dimensional. So, x power some x power v will be 0. So, you can choose k such that x power k v is becoming element of kernel x, and then if you apply that same x power k on this element, that is also going to be there inside your module. Okay, so let us go slowly. So, you have this v bar which is written as v plus some elements from that submodule generated by Vj. Now, it is easy to see that there exists k in Z plus such that x power kV is in the kernel x. So, that is just comes from the fact that capital V is finite dimensional and x power kV going to increase actually the eigen value, because we can choose V such that, okay, because this W is generated by V bar. So, V bar we want to write it as V plus something. So, we can choose this V coming from this eigenspace corresponding to M. So, basically from Vm. So, HV will become MV. Okay. So, now because we can choose this from here, it is clear that x power kV will have eigenvalue m plus 2k. Since they are all distinct, so there exists some k such that x power k plus 1 v is 0. So, that way you can choose this k. So, now this x power kV, if it is non-zero, then that tells you that m plus 2k becomes eigenvalue. Okay. Eigenvalue for the operator h, and this x power kV becomes highest weight vector. Highest weight vector inside capital V. So, that implies that V of m plus 2k will sit inside V, but that cannot happen because we already observed that for the only irreducible copy that can occur inside V is V of m. So, that forces that this k being 0. Okay. Now, if k is 0, so that means what? So, that means this x v is 0, that means V itself is actually highest weight vector, that forces that V itself highest weight vector of weight m. That means V has to be inside this summation Vj. Actually, it is one of this Vj. Okay, so V is exactly one of this Vj. But anyway, so that is not necessary. Actually, it does not need to be one of the Vj. It is going to lie inside the top weight space of summation Vj. Okay, sum of the top weight space, because it has weight m. So, it has to lie on the sum of the top weight spaces, which corresponds to m. Okay. So, now you can see that this V bar, it is coming from actually the quotient. So, that forces that V bar is non-zero inside the quotient, but we have proved that V bar is 0 because V is belonging to this summation Vj, submodule generated by Vj. So, that gives the contradiction that V bar is non-zero. So, this proves that V is exactly equal to summation Vj j ranging from 1 to r. So, now let us prove that it is indeed direct sum. For that purpose, if you take some non-zero vector w which is a non-zero vector inside Vj, let us not call it Vj, submodule generated by Vj intersection summation k not equal to j submodule generated by Vk. Okay. So, then what will happen, this being irreducible, so this forces that the intersection Vj intersection this summation Vk k not equal to j, this is entire module Vj. Okay. So, this is forced. So, now if you take this Vj, so this is now lies inside because this is there in this Vj summation Vk k not equal to j. So, this forces that this Vj is sum of scalar multiple of this Vk k not equal to j, which is contradiction because the weight of this is m. So, it has to lie on the top weight space which corresponds to m. So, that means this Vj must be the sum of scalar multiple of Vk k not equal to j, which is contradiction to the fact that they are all linearly independent. Okay, because we have chosen linearly independent vectors and then we have actually constructed the corresponding submodule generated by them. So, this cannot happen. So, that forces that this must be direct sum. So, that proves that V must be direct sum of this Vj ranges from 1 to r, each one of them is copy of Vm. So, basically we have r copies of this. So, basically it suggests some procedure to decompose capital V into direct sum of a sl2 irreducible representation. So, what is the procedure? You take V, first to write it as direct sum of V theta, theta comes from C where this is the generalized eigenspace corresponding to the eigenvalue theta for the operators C. Okay, then you focus on V theta. So, look at the kernel x inside this V theta. So, take basis of this, call it V1 etc. Vr. So, then this V theta is nothing but submodule generated by this Vj's j ranges from 1 to r. Okay. So, basically this decomposition and choosing this basis gives you the decomposition of capital V into direct sum of all these finite dimensional irreducible sub representations of capital V. So, this completes the proof of Weyl's theorem. Okay. So, this more or less actually completes the representation theory of sl2. So, we will actually see some consequences of this in the next class. So, we also need to make more observations about finite dimensional representations of sl2 using the facts that we have already proved. Okay, especially using this complete reducibility, we can immediately get many information about the given finite dimensional representation. Okay, I will stop here. We will continue in the next class. Yeah, thank you.